Hello and good afternoon, everyone. I welcome you all to this wonderful channel of Unacademy NEET English. I believe you all are doing good and having a great time. Well, my name is Khursheed Aalam, and you can also call me KK sir. Well, my dear lovely students, before we move ahead, I want quick confirmation that if you can see me clearly and you can hear me clearly, let me know in the chats first. Let me know in the chats that if I'm clearly audible and visible to each and every one. Let me know in the chats, quick. Let me know in the chats, my dear lovely students. Let me know in the chats if I am audible and visible to each and every one. If I am audible and visible to each and every one, let me know in the chats quickly. Okay, all right. I believe we are live now. And let me tell you, in today's session, we will cover complete 12th organic chemistry. So I hope you are super excited for this today's session, and I would want you guys to mark the attendance by smashing the like button, and I would want you guys to be with me till end of this session, because this session is going to be very much important. I hope your Josh is very high. Let me know in the chats, how is your Josh for today's session? Come on, quick. Let me know in the chats, how is your Josh for today's session? Come on. Come on. Come on, my dear lovely students. Today's session is very important. Today's session is very important as per your Re-NEET is concerned. Okay, I hope your Josh is very much high. Yes, one more thing. Do share this stream with everyone around so that they will get also benefited from this session. And I'm going to share the PDF of this session on a Telegram channel, and the link of that Telegram channel is, you can write down, the link of that Telegram channel is t.me/K, and after that all the alphabets are small. It's Sir Chemistry and then class. I'm going to share all the PDF of today's session on this channel. This is basically new channel, so you have to search this on, Google. So search this on Google and then click on link. If you have already joined, then it's okay, but if you have not joined yet, join it so that you will get the benefit of, every session. So this is t.me, address is t.me/KK Sir Chemistry class, but in KK Sir Chemistry class, first KK, they are capital, all other alphabets are small. Okay, so without wasting time, let's get started. Without wasting time, let's get started. Let's get started, my dear lovely students. Let's get started. So are you ready? Should we start today's session? Are you ready? Come on, let me know quickly. Are you ready for today's session? Are you ready for today's session? Now, first of all, as you know, we have completed structural isomerism and we have completed what we call conformational isomerism and geometrical isomerism in last session. Now today we are starting with optical isomerism. Now the question is, what are meant by optical isomers? These are the stereoisomers which differ in their behavior towards plane polarized light. Now the question is, what is meant by plane polarized light? Listen carefully. That light which oscillates in one direction or that light which oscillates in one plane is known as plane polarized light, and that light which oscillates in different directions is known as unpolarized light. So stereoisomers which differ in their behavior towards plane polarized light are called optical isomers, and the phenomenon is known as optical isomerism. Now have a look. Let's suppose this is substance or compound A in this, and in this it's compound B or substance B, and let's assume A and B are stereoisomers. Now have a look. When plane polarized light is passed through this substance, it gets deflected, rotated towards right direction. So the substance which rotates plane of plane polarized light towards right is known as dextrorotatory, denoted by small d, or it's denoted by a plus sign. Similarly, substance which is basically a stereoisomer, when plane polarized light is passed through that, if this substance deviates or rotates plane of polarized light towards left, then substance is known as levorotatory, denoted by small l or minus sign. Now have a look. If both these are stereoisomers, one rotates plane polarized light towards right, another rotates plane polarized light left towards left, that means these stereoisomers, they differ in their behavior towards plane polarized light, because one rotates it towards right and another rotates it towards left. Then such stereoisomers which differ in their behavior towards this direction or towards this sign, because one is plus, another is minus, they are known as what we call optical isomers. Similarly, if we are two stereoisomers C and D, but when light is passed through them, both rotates plane polarized light towards right. That means both are, say for example, dextrorotatory, but one rotates with lesser amount and another rotates this with larger magnitude. That means they differ in magnitude of rotation. Hence such stereoisomers are also known as what we call optical isomers. That means optical isomers can differ either in sign of rotation or in magnitude of rotation. After that, remember, if a molecule rotates plane polarized light in any direction, then that molecule is known as optically active molecule. And if molecule does not rotate plane polarized light, or net rotation of plane polarized light is 0, then we can simply say that molecule is optically inactive. And what is the cause of this optical activity? Why certain molecules rotate plane polarized light? Cause is chirality. Have a look what is meant by chirality. Basically, chirality is a phenomenon. So first of all, we should know what is meant by a chiral molecule. A molecule is said to be chiral if it is non-superimposable with its mirror image. That means a molecule and its mirror image should be non-superimposable. That means a molecule is said to be chiral if it is non-superimposable with its mirror image, and the phenomenon of that chirality is known as phenomenon of non-superimposability is known as chirality. But listen, my dear lovely students, this word chiral is basically derived from a Greek word meaning care, and care means hand. As we know, which means hand. The term refers to the concept of handedness, where an object or molecule like human hand is not superimposable on its mirror image. As we know, human hands are not superimposable with their mirror images, because these two hands are mirror images and these are not superimposable with respect to each other. So molecules which have property like that of hands are known as chiral molecules. That means those molecules which are non-superimposable with their mirror images are known as chiral molecules. After that, listen carefully. Which type of molecule can be called as a chiral molecule? Listen carefully. if a molecule does not have any chiral center. Now the question is, what is meant by chiral center? Chiral center means any center, any atom which is sp3 hybridized, and is attached to 4 different groups on 4 sides. So if molecule does not have any chiral center, generally such molecules are achiral molecules. Such molecules are not generally chiral molecules except few species. For example, if we are having cumulines with even number of pi bonds, spiro compounds with even number of amines rings. Similarly, we are having cycloalkylidines. That means those compounds which contain ring as well as a double bond. But if ring as well as double bond are even in number, ring plus pi bonds are even in number. Similarly, substituted by phenols. If these compounds are there, but if each end center of such compounds has different groups, then we know such compounds does not have any chiral center, but still they are chiral molecules. Say for example, this does not have any chiral center, but as we know, this is cumulene. What is meant by cumulene? Cumulene means those compounds in which pi bonds are present at adjacent positions. So here pi bonds are present at adjacent positions and they are even in number. Now we have to check only end center. This end center is having different groups A and B. This end center is having different groups. So whenever cumulene with even number of pi bond is there, if each end center has different groups, then such molecules does not have any chiral center, but still they are chiral. So this is a chiral molecule. Similarly, if we are having spiro compound means that compound in which, compound is bicyclic and there is at least one atom common between 2 rings. So if you are having a bicyclic compound, and in this bicyclic compound, if each end center, bicyclic compound in which one atom is common, that means spiro compound, but containing even number of rings, such compound does not have any chiral center, but if spiro compound with even number of ring is there, you have to check end center. If this end center is having different group, that means each end center is having different group. Remember, such compounds without any chiral center are still chiral molecules. Similarly, if you are having a ring as well as a pi bond, but both are what we call even in number, that means one ring, one pi bond, that means 1 plus 1 is 2, 2 is even. So if ring plus pi bond is even, at that time, once again you have to check end centers, and if each end center has different groups, such molecule is also chiral molecule. Similarly, substituted biphenyls are also chiral molecules, even though they do not contain any chiral center. So this is point number 1. But if compound is having only one chiral center, then most of the times, generally, such molecules, such compounds are always chiral molecules, except this amine and except this carbanion, where inversion takes place. So except these, because this is having chiral center, sp3 center, and 4 different groups are attached. 1, 2, 3, 4. 4 different groups are attached. So this is chiral center. This is having one chiral center, but still this molecule is not optically active. This is chiral, but this is not optically active. Listen, optically active molecules, chiral centers, those molecules which contain only one chiral center, they are generally optically active, but except these 2. These are having one chiral center. These are chiral molecules, but they are not optically active molecule because of inversion. I hope this is clear. You have to remember these things. After that, if a molecule contains more than one chiral center, then molecule may or may not be chiral. That depends on elements of symmetry, that depends on plane of symmetry, and that depends on center of symmetry. That means at that time we have to check plane of symmetry as well as center of symmetry. Remember these points. After that, my dear lovely students, after that we will be having chiral center or asymmetric center. I have already told you that chiral center or asymmetric center is that center which itself is sp3 hybridized, but is attached to 4 different groups. Have a look. This nitrogen is attached, this is sp3 center, and is attached to lone pair, hydrogen, deuterium, and CH3. That means 4 different groups. So this is chiral center. Similarly, this center, this carbon, is a chiral center or an asymmetric center because it is sp3 and is attached to 4 different groups. Similarly, if you look towards this, This is a chiral center. Similarly, if you look towards this, this is the chiral center. Why? Because this is Cl on one side, H on another side, this C having Cl on another side, this C having 2H on another side. That means this is chiral center, this is also chiral center. After that, count total number of chiral centers present in these molecules. Have a look. This molecule is having one chiral center, my dear lovely students. This molecule is having two chiral centers. One is this one and another is this one. Now, this is not the chiral center. Why is this not a chiral center? Have a look. This is having Br on one side, H on another side, but here it is CH2, CH2, CCl. Here it is CH2, CH2, CCl. That means this side and this side, they are identical sides. Hence, this is not having the chiral center. So, this is not the chiral center. Similarly, this is not the chiral center because this is having Cl and H. But on this side it is CH2, CH2, then CHBr. On this side it is CH2, CH2, CHBr. That means this side and this side, they are identical groups or identical sides. Hence, this is not having any chiral center. So here chiral center is 0 in number. Here it is 1 in number. Here it is 2 in number. Here chiral centers are 3 in number. After that, this cannot be a chiral center because this is sp2 hybridized, as it takes part in what we call resonance. Because all those atoms which take part in resonance, they are sp2 hybridized. So this is not having any chiral center. So this is having 0 chiral center. This is the 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 chiral center. This is not, because this is H and H identical. So this is having 4 chiral centers. I hope this is clear. After this, we will be having elements of symmetry. So, one element of symmetry is plane of symmetry, also known as sigma plane or mirror plane, and plane of symmetry is, written as P.O.S in short form. So, what is plane of symmetry? It's an imaginary plane which divides an object or a molecule into two equal halves such that one half is exactly mirror image of another half. Listen carefully. Have a look. If we try to imagine a plane over here, this plane divides this molecule into two equal halves such that above half and below half, they are mirror image of each other. That means this is having plane of symmetry. So plane of symmetry is present in this. But in this molecule, plane of symmetry is absent. Plane of symmetry is absent in this molecule. Listen carefully. Here, this can be the plane of symmetry. This can be the plane of symmetry because it divides the molecule into two equal halves such that right side is exactly mirror image of left side. So this is having plane of symmetry. So plane of symmetry here is also present. Now, what about this? This Cl is actually above the plane like this, and this Cl is below the plane like this. So we will simply put an imaginary plane like this. When an imaginary plane like this is drawn, it divides the molecule into two equal halves. Look, so this molecule is divided into two equal halves. So we can simply say plane of symmetry is also present in this. But here, plane of symmetry is absent because we cannot divide this molecule into two equal halves. Let me know in the chats quickly. Am I clear till now? Is this part clear to you? Let me know quickly. After that, we will be having another, that is center of symmetry. What is center of symmetry? It's simply an imaginary point or imaginary center. This is also known as center of inversion. So imaginary point or imaginary center, listen carefully, through which when lines drawn on one side, say for example, I have drawn this line above the plane because BR is basically above the plane. When lines drawn on one side and then produce an equal distance on opposite side. What is the opposite side of above the plane? Above the plane, opposite side means below the plane. Now, so you have to check one side above the plane, another below the plane. That means two sides should be opposite. That means at 180 degree. So two sides, opposite two sides. Number one, equal distance. Number second. Number third, identical atoms or identical groups. So similarly, if we draw a line through this point, this is below the plane. Now we have to draw a line opposite to this, that means above the plane. And this is pointing, equal this is touching equal points or equal atoms. Similarly here, this is above the plane, this is below the plane. Similarly here, this is below the plane and this one is above the plane. So from this point, when we draw line on one side and produce an equal distance on another side, it simply produce an equal distance on another side, it simply meet identical points. That means identical atoms or groups. Hence we can simply say COS is present in this, center of symmetry is present in this. But listen, center of symmetry is always absent if ring is made up of, I mean say odd number of carbons. So we can simply say center of symmetry over here is absent. So you can note down this, that center of symmetry is always absent in rings with odd number of atoms. Now, what about this, my dear lovely students? Have a look. So if we draw line from this on one side, then draw line on opposite side, it will meet identical atoms. Similarly, it will meet identical atoms. Here on above the plane, it is H, and below, that means below the plane, that means opposite to this, it's also H. Here below the plane, it's CH3. Opposite to this is also CH3. That means COS is also present in this. What about this? What about this? Have a look. Here above the plane, it is Cl. Opposite to this is below the plane. So below the plane is also Cl. That means on opposite sides at equal distance, identical groups are there. Similarly, this opposite to this is 180, this one oxygen, oxygen, carbon, carbon. So it is basically that center from which when lines drawn on one side produce an equal distance on another side, they will meet identical points. Hence COS is also present in this. COS is also present in this. What about this? Imaginary center. Draw a line on one side. This is above the plane, this is below the plane. It's meet, I mean say this line will meet identical groups over here. Similarly, identical groups are touched. That means this center, this imaginary center is center of symmetry. So center of symmetry is also present in this. Center of symmetry is also present in this. What about this? What about this? Have a look. This is cumulene with odd number of pi bonds. Have a look. If this is the center, this is H, opposite to that is H, opposite to this Cl is also Cl, so COS is present. But remember, when you are having cumulene with even number of pi bond, you are having spiro compound with even number of, I mean say rings, you are having, I mean say substituted biphenyls. At that time, these groups are basically perpendicular to each other in different planes. That means if these two are present on the board, these two should be above and below the plane. That means they are perpendicular. And remember, whenever you are having groups perpendicular to each other, COS is always absent in that. That means COS is absent in cumulenes with even number of pi bond. COS is absent in spiro compound with even number of pi bond. COS is always absent in what we call substituted biphenyls. I hope this is clear. Now, what about this? So COS here is absent. COS here is absent. Now, what about this one? Have a look. Have a look. It's C and C on opposite sides. It's NH, NH on opposite side. Now, it's C and C on opposite side. Above the plane it's Cl, below the plane it's also Cl, below the plane it's H, above the plane it's also H. So COS is also present over here. Listen, one more important point. One point, if groups are perpendicular to each other, COS is absent. Second point, if ring is made up of, I mean say odd number of atoms, COS is absent at that. And number third, in case of Fischer structure, COS is always absent. Why is it so? Have a look. It is basically structure like this. Structure is actually like this. Structure is actually like this. Structure is actually like this. Groups which are present on vertical line, they are considered behind the plane. And groups which are present on horizontal line, they are considered always above the plane as per Fischer structure is concerned. So, can we say this is the center? On one side it is OH, on another side it is H. Can we say like that? Can we say like that? No, because if say for example you are having a structure on like this, have a look. If you are having structure like this, It is OH on this side, OH on this side, H on this side. You can never say that these two OH are opposite, these two H are opposite. Why? Why they are not opposite? Because this is above the plane, this is also above the plane. That means this is above the plane, above the plane, above the plane, above the plane are not opposite. There should be two groups opposite, equal distance, and those lines will meet identical, points through this center. So that's why this, you have to remember 3 points. Number one, COS is always absent if ring is made up of odd number of atoms. Number one. Number second, COS is always absent if you are having a fissure structure. If you are having fissure structure, COS is always absent, and COS is always absent if groups are at perpendicular, because groups should be at 180 degree. If groups are present at 90 degree, they are not opposite with respect to each other. And for COS, groups should be opposite, and the center through which lines will pass on one side and on another side will meet identical points. That's why you have to remember these points. After that, my dear lovely students, there is a very important, concept, and that is configuration around chiral center. And configuration around chiral center are of two types. One is absolute configuration or actual configuration. Another is relative configuration. So let's discuss absolute configuration, also known as capital R and capital S configuration. Capital R and capital S configuration. Listen carefully. Capital R, it has basically a Latin word, rectus. It came from that, which means clockwise. Which means clockwise, or we can simply say right hand side direction. Right hand side direction, or right side direction. Clockwise or right side direction. Number second, S came from sinister. This is once again a Latin word. So these are Latin words, rectus, short form R, sinister, short form S. Sinister means anti-clockwise or left side direction or left hand side direction. Now, direction of what? Direction of what? Direction of groups around chiral center. Direction of groups around chiral center whose priority, whose priority is 1, 2, 3, 4, because 4 groups are there. There will be chiral centers. Chiral center is always attached to 4 different groups. So those groups have different priorities like 1, 2, 3, 4. Now have a look. What we have to do is listen carefully. Listen carefully. Listen carefully. Now listen carefully. Say for example, this is the chiral center. This is the chiral center. Now listen carefully. This is the chiral center. This is the chiral center. Say for example, it's having 4 groups A, B, C, D. First of all, this is sp3 hybridized center and 4 different groups are attached. So let us say this is a chiral center. Now, this chiral center is attached to 4 different groups. We first have to give the, priority. Say for example, let's say priority of A is 1, priority of, B is 2, let us say priority of D is 3, priority of, C is 4. What we have to do is, we have to check direction. We have to check direction of 1, 2, and 3 group. That means, this is actually direction of groups around chiral center, but they are 4 in number, but this direction is only of 1, 2, and 3. This is direction of 1, 2, and 3. Listen carefully. Direction of group number 1, that group which is having priority 1, that group which is having priority 2, and that group which is having priority 3. That means you have to check direction of 1, 2, and 3. And if direction of 1, 2, 3 is, clockwise, then it can be 2 things. It can be R in actual sense, or it can be R but which changes to S. Listen carefully, listen carefully. Similarly, if it is 1, 2, 3, direction is anti-clockwise, then it is actually S, but sometimes it changes from S, we say it is R. Now, listen carefully, listen carefully. What is this? Listen. If you are having a fissure structure, this is a fissure structure. In case of fissure structure, listen, very, very important point. Fourth priority group should be present on vertical line. It should be present on vertical line. Whenever your fissure structure is such that fourth priority is present on vertical line, at that time when direction of 1, 2, 3 is clockwise, it is R. And if it is anti-clockwise direction, then it is S. Listen carefully. But if fourth priority is present on, say horizontal line, in case of fissure structure, if it is present on horizontal line, then 1, 2, 3, if direction of that is clockwise, it should be R, but it will not be R, it will be S at that time. Similarly, anti-clockwise direction should be actually S, but it will not be S at that time, it will be R. This change in configuration, but when fourth priority group is present on horizontal line, this is known as golden rule. This is known as golden rule. So where we have to use golden rule? We have to apply golden rule in case of fissure structure, but when least priority is present on horizontal line. Let me know in the chats first, is this clear? Is golden rule clear to you? Is golden rule clear to you? Is this clear to you? Is this clear to you? Is golden rule clear to you? Is R and S clear to you? So at that time you have to use golden rule. You have to use golden rule. Now, let me know in the chats, is this clear? Is this clear? Let me know, because this is very, very, very important. If it is clear that when it is R, when it is S, then I will move ahead. Let me know in the chats quick. Let me know in the chats quick. Is this clear to you? Okay, listen carefully. Listen carefully. First of all, you have to find out chiral center. After that, chiral centers will be having 4 different groups. Then we will give priority to them. Say for example, first is this priority, say this group is having first priority, let's suppose. This is having second priority, let's suppose. This is having fourth priority, let's suppose. And this is having third priority, suppose. Now, we know fissure structure means vertical and horizontal structure. If fissure structure is such that fourth priority group is present on vertical line, it's present on vertical line, then you have to check 1, 2 and 3. For example, this is 1, this is 2 and this is 3. Can I say 1 is here, then 2 is here on this side, 3 is on this side. When fourth priority was on vertical line, now look towards 1, 2 and 3. Which type of direction is this? This is clockwise direction. At that time, clockwise direction is known as R. At that time, we can simply say this as R. I hope this is clear. But if you are having like this, chiral center is like this. This is 1. Say for example, this is A is having 1 priority. This is B. Let us suppose B is having second priority. Suppose this is, C. This is C and this is D. Listen carefully. This is C and this is D. C is having fourth priority and D is having third priority. Now, look towards this and tell me fourth priority is on horizontal line. We know 1, 2 and 3. We have to check direction of 1, 2 and 3. Now tell me, if this is 1 is on this side, 2 is on this side, 3 is on this side. So what is the direction? What is the direction of 1, 2 and 3? It is clockwise. So I will say it is clockwise. But listen, say 1, 2, 3. If 1, 2, 3 is present on a clockwise direction, then it can be actually R. It can be actually, because clockwise means right side direction and that means actually R. But here it will not be R, it will be S. It will not be R, it will be S. Why? Because whenever fourth priority is present on horizontal line, you have to change configuration. You have to change configuration means you have to use a rule known as golden rule. You have to use a rule known as golden rule. I hope this is clear. So now tell me when to use golden rule. Golden rule is applicable only in case of Fisher structure, and that too when fourth priority group is present on horizontal line. At that time, whatever will be the direction of 1, 2, 3, say for example, if it is 1, 2, 3 direction is clockwise, it should be R, but we have to change that to S. Similarly, 1, 2, 3 on anti-clockwise means S, but in case of this golden rule, we have to change that from S to R. I hope this is clear. I hope this is clear. Then, my dear lovely students, listen carefully. Listen carefully. Say for example, you are having this structure. You are having this structure. This structure is known as dash and wedge structure. This is known as dash and wedge structure. Say for example, this is priority number 1, this is priority number 2, this is priority number 3, this is priority number 4. Now, in case of dash and wedge, listen carefully. In case of dash wedge structure, fourth priority group should be present on dash bond. It should be present on dash bond. Now, if it is present on dash bond, we have to check 1, 2 and 3. We have to check direction of it. If direction of 1, 2, 3 is clockwise, we call that as R, and if it is having anti-clockwise direction, at that time we call configuration as S. Now is this clear? Is this clear? Now let me tell you once again. In case of Fisher structure, if fourth priority group is present on vertical line, then direction of 1, 2, 3, if it is clockwise, it is R. Direction of 1, 2, 3, if it is anti-clockwise, it is S. But if fourth priority is not present on vertical line, it is present on horizontal line, then 1, 2, 3 does not, if 1, 2, 3 direction is clockwise, it does not mean at that time R, we have to change it. We at that time call it as S configuration. Similarly, if 1, 2, 3 is present in anti-clockwise direction, but fourth priority is present on horizontal line, we call at that time that as R instead of S, and that is known as golden rule. Now, after this, if I mean to say for example, this is the carbon and we are having A, B, C, D groups around this, that means this is the chiral center. Then if A is having first priority, B is having second priority, D is having third priority, C is having fourth priority, and our fourth priority is present on dash bond, at that time, if direction of 1, 2, 3 group, is anti-clockwise, we will call at that time as S. If 1, 2, 3 is clockwise, we will call that as R. After that, my dear lovely students, listen carefully. If you are having a group like this, say for example, this is A, this is B, this is D, and let us suppose this is E, and suppose this is 1, this is 2, this is 4, this is 3. Now, have a look, listen. Fourth priority group should be present on dash bond. It should be present on dash bond. Fourth priority group should be present on dash bond. But here, it is not present on dash bond. Then never use golden rule over here. Simply what you have to do is, you simply give one interchange, that's it. Have a look. Give one interchange between that atom or that group which is having fourth priority. When fourth priority is not present on dash bond, now you will simply do one thing, give fourth priority. Now from this to this, you have to interchange. You have to interchange groups in such a way. You have to interchange groups in such a way. Only one interchange. Interchange groups in such a way so that fourth priority group is, fourth priority group comes at dash bond. Give one interchange between groups so that fourth priority comes to dash bond. That means I have to interchange D and E, that means 4 and 3. So can I say it is now D, it is now E. So what was the priority of A? It was 1. What was the priority of B? It was 2. What was the priority of E? It is 3. What was the priority of D? It's 4. Now our aim is now fulfilled because fourth priority should be present on dash bond. Now aim is fulfilled. Now what is the direction of 1, 2 and 3 now this time? 1, 2 and 3 is, say anti-clockwise means S. So this is S. But after one interchange, this is S. Hence, this molecule is having configuration R. If you have to find out configuration of this molecule, you cannot find its configuration directly. Give one interchange from this, which is, in which fourth priority is present in dash bond. After that, you can find out configuration of this, and reverse of that is over here. Or if this is S, this will be R. If this is R configuration, this will be having S configuration. I hope this is clear. I hope this is clear. I hope this is clear. Let me know quickly, is this clear? Is RS clear to you as per Fisher structure is concerned, as well as dash and wedge is concerned? This is more than sufficient. This is more than sufficient. At the rate of Gary Raman, it's more than sufficient. Is this clear? Electronic effects that have already done, beta, in class 11 session. Okay. Now listen. Let me show a few examples so that this will be understood to you. Now have a look. Have a look. Have a look. If I write an example like this, this is I, this is Br, this is F, and this is Cl. Suppose we have to find out, R and S configuration for this. For that, we have to identify, is this the chiral center? Answer is yes, this is the chiral center. Why? Because this is sp3 center and 4 different groups are attached. Point number 1. Point number 2, we have to prioritize these groups which are surrounding this chiral center. That means we should prioritize these groups, and we know priority came from CIP rules. We have already discussed such rules in previous session when we discuss EZ configuration in case of alkenes. Now, let me tell you once again, rule 1 was, what was rule 1? Rule 1 was priority is directly proportional to atomic number. Priority is directly proportional to atomic number. That means here, groups which are attached to chiral center, or atoms which are attached to chiral center, that atom or that group which is attached to chiral center, whose atomic number is highest, got highest priority. Now we know iodine, bromine, chlorine and fluorine is there. Iodine is having higher atomic number, so this is 1. Bromine is having lower atomic number than iodine, but higher than chlorine and fluorine, that is why it is 2. Then it is chlorine, then it is fluorine. Now tell me. 1, 2, 3, 4 is there. So chiral center, 4 groups with priorities. Now tell me, is fourth priority present on horizontal line or vertical line? Because this is Fisher structure. Is fourth group present on horizontal line or vertical line? Let me know quickly in the chats. Is fourth priority present on horizontal line or a vertical line? Let me know quickly. It's present on vertical line. When fourth priority is present on vertical line, at that time, what we have to do is, we have to check priority 1, priority 2, priority 3, we have to check their direction. We have to check direction of 1, 2 and 3. Now tell me, what is the direction of 1, 2 and 3? It is clockwise. Now listen, clockwise direction of 1, 2, 3 When least priority or fourth priority is present on vertical line, means it's R, which clearly indicates its configuration is R. So its configuration is R. After that, let's take another example. Let's take another example. Say, for example, this is an example number 1. This is an example number 1. Let's take another example, example number 2. Have a look, so that it is clear to you. Now, this is I, this is Br, this is Cl, and this is F. Once again, what we have to check is, first of all, we have to check, is this chiral center? Answer is yes. After that, when this is the chiral center, now prioritize these groups which are attached to chiral center. This is 1, this is 2, this is 3, and this is 4. This priority is on the basis of rule number 1, because priority is directly proportional to atomic number. That group which is having that atom which is having highest atomic number got highest priority. Now, tell me, what is the direction of 1, 2, and 3? Have a look. What is the direction of 1, 2, and 3? 1 is on this side. Second priority group is on this side. Third priority group is on this side. So what is the direction of 1, 2, and 3? This direction means anti-clockwise direction. Now listen carefully. Direction is anti-clockwise and fourth priority is present on vertical line. That means clockwise means R, anti-clockwise means S. So clockwise means R, anti-clockwise means S. So it is what we call S. So 1, 2, 3 clockwise means R if least priority is present on fourth line. 1, 2, 3 anti-clockwise means S if least priority is present on vertical line. Is this clear? Is this clear, so that I will move ahead? Is this clear? Is this clear, so that I will move ahead? Let me know quickly. Let me know quickly, my dear lovely students. Let me know quickly in the chats. Is this clear? Is this clear? Is this clear? Is this clear? Let me know quickly. Come on, come on, come on, everyone, everyone, everyone. That's great. That is great. That is great. That is great. That is great. Now, let's take another example. 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 Have a look. Example number 3. Let's take another example like this. Suppose you are having this one. This is I, this is Br, this is Cl, and this is F. Now tell me, my dear lovely students, first of all we have to check, is this the chiral center? Answer is yes, this is the chiral center. Now, priority on the base of rule number 1, this is 1, this is 2, this is 3, this is 4. So what is the direction of 1, 2, and 3? Have a look. 1 is here, second priority is here, third priority is here. So what is this direction? This direction is clockwise. So this direction is clockwise. So it should be, because clockwise means R, it should be R. But we have to check. Is fourth priority group on vertical line? Answer is no. Fourth priority group is present on horizontal line. So I will write down, fourth priority group is present on horizontal line. Whenever fourth priority group is present on horizontal line, use golden rule. Now what is meant by use golden rule? That means if clockwise direction is there, it means it is R. You have to change this. That means it will not be now R. Its actual configuration will be S. It should be R. But as this is present, fourth priority group is present on horizontal line, we have to change this. That is what we call golden rule. So its configuration will be S. Now after that, fourth one. Say for example, this is I, this is Br, this is Cl, this is F. Now tell me, is this the chiral center? Answer is yes. After that, priority 1, 2, and this is 3, this is 4. Now we have to check only 1, 2, and 3. 1 is on this side, 2 is on this side, 3 is on this side. Now what is the direction between 1, 2, and 3? What is the direction? 1 to 2, 2 to 3. It is anti-clockwise. But anti-clockwise means it should be S. Anti-clockwise means it should be S. But we have to check fourth priority group. If fourth priority group is present on vertical line, S remains as it is. But fourth priority group is not on vertical line, it is present on horizontal line. Whenever fourth priority group is present on horizontal line, we have to change the answer. That is what we call golden rule. That means we have to use golden rule. What is golden rule? Whatever is the answer, change this. That means it is S. So change it. Actual answer will be R. So its actual configuration is R. I hope this is clear. I hope this is clear. I hope this is clear. Is this clear? Is this clear? So, in nutshell, you can remember like this. Whenever fourth priority group is present on vertical line, clockwise, 1, 2, 3 clockwise means R, and 1, 2, 3 clockwise means S. But if fourth priority group is present on horizontal line, 1, 2, 3 clockwise means S, and 1, 2, 3 anti-clockwise means R. After that, there is another rule, rule number 2. Rule 2 says, if similar atoms of different groups are attached to a chiral center. Then atom next to these atoms is considered. These atoms is considered. Till first point of difference is reached. And then use rule number 1. That means then you have to give priority according to rule number 1. That means according to atomic number. So what is this? Have a look. Suppose you are having I, you are having H to this, and then this is having CF3, or you can say it's having CF3. This is having CF2 and H. Now, first of all, is this the chiral center? Yes. Why? Because it's sp3 hybridized and is having 4 different groups. So this is the chiral center. Now to this chiral center, atom I is attached. Here atom C and atom C is attached. Here it is atom H. First of all, among these 4 atoms, I, C, and H, I is having highest priority. So this is 1. H is having lowest priority. That means, lowest atomic number. So it's having 4 priority. Now, this C and C, these 2 atoms are same atoms, but these groups, this CF3 group and CF2H group, they are different. So these are the atoms of different groups which are attached to, chiral center. This is atom having atomic number 6, atom having atomic number 6. So on the basis of rule number 1, you cannot distinguish these 2 atoms. Then what we have to do? We have to go to next atom. So what is the next atom over here? Let me write down that set over here. It is F, F and F. What about this? Here it is F, F and H. First you have to write down that atom which is having highest atomic number. Among H and F, F is having highest atomic number. That's why I wrote F first. Now compare these two. This is F, this is F. Same atoms, there is no point of difference. After that, go to next atom. This is F, this is F. Once again, same atom, there is no point of difference. After that, this is F, this is H. So point of difference is there. This is F, this is H. So if similar atoms of different groups are attached to a chiral center, then atom next to these atoms is considered. Atom next to these atoms is considered till first point of difference is reached. Then priority is given according to rule number 1. Then use rule number 1. That means priority is given on the basis of atomic number. This is F, this is H. This is having highest atomic number. So if this is 1, this is 4, among these 2, this will be 2 and this will be 3. So now tell me, what is the direction? What is the direction between 1, 2 and 3? Have a look. This is 1, This is 2 now, and this is 3. Have a look. This is 1, this is 2, this is 3. So what is the direction? Direction is clockwise. Clockwise should be R. Now the question is, should it be R or should we change it from R to S by using golden rule? That will be decided by fourth priority. Fourth priority is present on vertical line. So I will write down fourth priority group is present on vertical line. When fourth priority group is present on vertical line, there will be no, say golden rule. That means whatever is the configuration, that is the correct answer. So its configuration is simply R. Its configuration is simply R. I hope this is clear. Now, if same example is like this, now this is I, this is H, this is CF3, and this is CF2H. Now, we know already from this example that this is first priority group, this is second priority group, this is third priority group, and this is fourth priority group. Now tell me, what is the direction of 1, 2, and 3? This is 1, this is 1, this is 2, and this is 3. So what is the direction of 1, 2, and 3? 1, 2, and 3 is clockwise. 1, 2, and 3 is clockwise. So let me write down clockwise. But clockwise should be R, but it changes from R to S. Why it changes from R to S? Because fourth priority group is present on horizontal line. It is present on horizontal line. I hope this is clear. That is why its configuration is S. Let me know quickly, is this clear? Let me know quickly, is this clear? Come on, tell me, is this clear to you? Let me know quickly. Come on, my dear lovely students, let me know quickly, is this clear? Come on, tell me. Yes, clear. God bless you. After that we will be having another rule. And what is that rule? That is rule number 3. Rule 3 says, if isotopes are attached to chiral center, then simply remember, priority is directly proportional to mass number at that time. So we will simply say priority is directly proportional to mass number at that time. Now have a look. Let's take a simple example of this. This is I, this is D, deuterium, this is protium, and this is bromine. As this is the chiral center, this is I, Br, so these two are hydrogens, but this is isotope of hydrogen, these two are two isotopes of hydrogen, so this is having highest atomic number. After that it is bromine, but these two hydrogens, that means protium and deuterium, they are having same atomic number, so they cannot be distinguished on the basis of atomic number. We cannot give 3 to this or 3 to this on the basis of atomic number. So on the basis of mass number, that group which is having highest mass number, that isotope which is having highest mass number is having highest priority. So among these two, this is having highest mass number, so we will give 3 to this, 4 to this. Now tell me, what is the direction of 1, 2, 3? What is the direction of 1, 2, and 3? This is 1 on this side, 2 is on this side, 3 is on this side. So what is the direction? What is this direction? This is anti-clockwise direction. Anti-clockwise direction means S. Now the question is this S? Will this S remain as S or should we change this? That depends on fourth priority group. Fourth priority group is present on vertical line. Whenever it is present on vertical line, we do not have to change the configuration. So its configuration is what we call S. Its configuration remain as it is. Now, if the same example is there, this is I, this is D, this is, what we call Br, this is H. Same example. This is 1, this is 2, this is 3, and this is 4. Now tell me, what is the direction of 1, 2, and 3? 1 is on this side, 2 is on this side, and 3 is on this side. So this is clockwise. So clockwise means it should be R. But should will it remain as R or should we change this? That depends on fourth priority group. Now have a look. Fourth priority group is present on horizontal line. On horizontal line. Whenever fourth priority group is present on horizontal line, we have to use golden rule. And what is golden rule? Whatever is the configuration, change that. That means its actual configuration is S. So this is S. I hope this is clear. I hope this is clear. Let me know quickly, is this clear? Is this clear? Because most of the students have given me the right answer. That means this is clear to them. I hope this is clear. After that, my dear lovely students, listen carefully. After that, we will be having another rule, and that rule is rule 4. What is rule 4? Groups, if groups attached to chiral center, if groups attached to chiral center contains double bond or a triple bond, then each atom of double bond is duplicated and each atom of triple bond is triplicated. And then priority is given according to rule 1. Priority is given according to rule 1. Now the question is, what is meant by this? Have a look. If you are having like this is I, say for example this is H, this is C double bond O and H, and this is C triple bond N, then this chiral center contains this group which is already having double bond and this group which is already having triple bond. Then what we have to do is we have to duplicate these two atoms which form double bond, and we have to triplicate these two atoms which form triple bond. How to duplicate and how to triplicate? Have a look. First of all, I will write down I and H as it is. After that, I will mark those two atoms which form double bond. These are the real atoms which form double bond. So what will we do is we will form a single bond between those two atoms which form double bond, and we will mark them. So these were the atoms which were forming double bond, but in this case they are having single bond. What does that mean? That means this carbon is having one atom. This carbon is having one bond lesser. So this is having one bond lesser, so give it one bond. This oxygen is having one bond lesser, give it also one bond. But this is having one bond lesser than oxygen. This is having one bond lesser, but that bond has been, this carbon was having two bonds with oxygen, but here it was having only one bond with oxygen. That means one bond with oxygen has been decreased. So give one oxygen to it. Similarly, this oxygen forms two bonds with carbon in this structure, actual structure, but here it forms only one bond with carbon. So give another carbon to it. So these atoms are not present. These are the atoms which we have been added, which we have added. These atoms are known as phantom atoms. So satisfy the valency of phantom atom. We know oxygen forms two bonds. It's only one over here. Give hydrogen to it. Carbon forms four bonds. It's only one bond. Give three bonds to it, three hydrogens to it. So it is like this. So oxygen has been duplicated twice. One is real, one is phantom. Carbon has been duplicated. One is real, one is, phantom atom. Now after that, have a look. This carbon and nitrogen forms three bonds. What we have to do is, first of all, we will form single bond between them. After that, in total, this carbon should form three bonds with nitrogen. But here it is one. After that, I will form two more single bonds with two nitrogens. So carbon forms three bonds with nitrogens. Carbon forms three bonds with nitrogen. This nitrogen forms, real nitrogen forms three bonds with carbon. But here it forms only one bond with carbon. So you can form two more single bonds with two carbons. So it will be like this. So these two nitrogens and these two carbons are phantom atoms. So satisfy the valency. Valency is satisfied like this. You just satisfy the valency. Now, have a look now. Have a look now. This is the chiral center. To this chiral center, this is I, this is C, and this is H. Can I say I is having highest number, atomic number? So this will be 1. After that, 4 is having lowest atomic number. So this H is having lowest atomic number. So this is 4. After that, these two are having similar atomic number. So I will go to next atom. Which atom is next to this? It's oxygen, hydrogen and oxygen. But we will write down first which is having highest atomic number. That means oxygen first. After that, second oxygen. After that, I will write down hydrogen. So I have to write down this, and I mean to say this and this oxygen. I mean say this and this, which are directly attached to this carbon. Here, which atoms are directly attached to this carbon? It is this nitrogen and this nitrogen. So I will write down over here N and an N. Now compare one by one. This is oxygen, this is nitrogen. First point of difference is there. Atomic number of oxygen is higher than this. That is why this becomes 2, this becomes 3. So what is the direction of 1, 2 and 3? Have a look. 1 is over here, 2 is here, 3 is here. So it is clockwise direction. Clockwise direction means R, and it remain as it is. Why? Because fourth priority group is present on vertical line. So we cannot use golden rule over here. So its configuration is R. Now, but we don't have this much of time over there. That's why let's take a simple trick over here. Whenever you are having a triple bond between two atoms and there is a double bond between similar atoms and there is single bond between similar atoms, then this will be having highest priority, then this, then this. That means, for example, if you are having carbon-carbon triple bond, I'm not satisfying the valencies over here. Say for example, carbon-carbon triple bond is there, carbon-carbon double bond is there, carbon-carbon single bond is there. Triple bond got preference over double bond got preference over single bond. But if all the atoms which forms triple bond, similar atoms form double bond, similar atoms form, I mean say single bond. But, if you are having a carbon-carbon triple bond, then on the other side, you are having carbon double bond oxygen. There, triple bond is between carbon-carbon, double bond is between carbon-oxygen. That means these are different basically groups. Now, listen carefully. At that time, give priority to C double bond O. Similarly, if you are having carbon-carbon triple bond, carbon double bond nitrogen, give preference to or priority to carbon double bond nitrogen. Similarly, if you are having carbon-carbon triple bond, carbon triple bond nitrogen, similarly highest priority will be of carbon triple bond nitrogen. Similarly, if you are having carbon double bond oxygen on one side and carbon double bond nitrogen on one side, give priority to carbon double bond oxygen at that time. So you can simply correlate it simply. Now similarly, if you are having carbon double bond oxygen and carbon triple bond nitrogen, give priority to carbon double bond oxygen. So you can directly use this and give priority. So for example, what will be the configuration of this molecule? Say for example, you are having CN, that means you are having C triple bond N, you are having C double bond O and then NH2. Then you are having, have a look, C double bond O and then Cl. You are having, say for example, C triple bond C, H. Now, have a look. What we have to do is, this is chiral center. First of all, have a look. This is carbon triple bond nitrogen. This is carbon triple bond carbon. This is having higher priority as compared to this. But this is carbon double bond oxygen, carbon double bond oxygen. These two are having higher priority than these. So these two are having higher priority. That means one will be 1, another will be 2. Then this will be 3 and this will be 4. Simple. Now among these two, C double bond O means this oxygen will be duplicated. So in this carbon, you have to join 2 oxygen. So I will write down O and O. Why O and O? Because this O is duplicated. After that, it is this nitrogen which is attached to this. But here, it is OO and Cl. Among OO and Cl, it is Cl then it is O, then it is O. Why? Because you have to write down that group which is having that atom first, which is having highest atomic number. Now compare this. This is oxygen, this is chlorine. Chlorine is having higher atomic number. So this is 1, this is 2. So this is 1, 2. This is N, N, N if you want, because nitrogen forms triple bond, so it will be thrice. It will be triplicated. Here it will be C, C and C. So you can check, you can easily check. This is oxygen, chlorine, oxygen, nitrogen and carbon. Chlorine, oxygen, nitrogen and carbon. Chlorine gets first priority, nitrogen gets, oxygen gets second priority, nitrogen third, carbon fourth. So 1, 2, 3. 1, 2, 3 will be like this. This is 1, this is 2, this is 3. And then this is what we call anti-clockwise direction. Anti-clockwise direction means S. Now, where is fourth priority group? Fourth priority group is present on horizontal line. Now, if fourth priority group is present on horizontal line, use golden rule. Use golden rule means change this configuration to R. That means its actual configuration is R. I hope this is clear. So this was all about R and S configuration in case of Fischer structure. Now my dear lovely students, have a look. If you are having this one, this is, say for example, I, this is Br, this is what we call Cl, and this is F. Now what you have to do is simply prioritize these groups. This is priority number 1, this is priority number 2, this is priority number 3, this is priority 4. Have a look. Fourth priority is present on dash bond. Now check only 1, 2 and 3. What is the direction of 1, 2 and 3? 1, 2, 3 is anti-clockwise. Anti-clockwise means it is S. So it is S. So its configuration is S. But if you are having like this is I, this is, say for example, F, this is suppose Cl, and this is Br. Now this is 1, this is 2, this is 3, this is 4. Fourth priority should be present on. Fourth priority should be present on dash bond. That means we have to first interchange this. We will interchange. First interchange simply. First interchange between that group that which is having fourth priority. That means between 4, because I want 4 on dash bond. That means 4th and 2. I have to interchange 4 and 2. I will interchange 4 and 2. That means here it was 1, it remain as it is. Here it was group 3, it remain as it is. But here it was 2, now it is 4 now. It was 2, but it is 4 now, because 4 and 2 have been basically exchanging their position. So this is 2. Now tell me, what is the, because now fourth priority is on dash bond. Now what is the direction of 1, 2 and 3? 1, 2 and 3 is anti-clockwise. Anti-clockwise means it is S. So this is S. But question was what is the configuration of this? Its configuration will be opposite to this one. This is S, that means this is R. But never use golden rule. That means whenever your fourth priority is not present on dash bond, you have to interchange in such a way so that fourth priority goes to dash bond. Then you have to find out configuration. Whatever is the configuration, you just reverse that configuration. That will be the configuration of this question. I hope this is clear. Similarly, if you are having like this is I, this is, I mean to say F. Say for example, this is Cl, and let us suppose this is Br. Tell me, is fourth priority present on dash? Is fourth priority present on dash? Answer is no. Now what we have to do is we have to interchange. Now we have to interchange only one interchange. Now interchange fourth and that which is present on dash bond, that is 3. That means 4 and 3 here. 4 and 2. Why 4 and 2? Because 2 was present on dash bond. Here 3 is present on dash bond. That's why 4 and 3. Now what will be the, say compound now? It will be 1 on this side, 2 on this side, because they do not have changed their position, but their position has been changed. That means now here it will be 4, it is 3 over here. So what is the direction? 1, 2, 3, anti-clockwise direction. Anti-clockwise means this is S, but as this is S, R, this molecule, it will be R. I hope this is clear. I hope this is clear. I hope this is clear. Now next is relative configuration. Another is relative configuration, and that is, say capital D and capital L configuration. And in case of carbohydrates, say for example in carbohydrates, D and L in case of carbohydrates, polyhydroxyaldehydes and ketones containing at least one chiral center. So have a look. In case of carbohydrates, if you are having a Fischer structure like this, in which CHO is present on top, CH2OH is present on bottom, then listen carefully. CHO Fischer structure is such that CHO on top, CH2OH on bottom. Then this structure, these structures are known as glyceraldehydes. So this is glyceraldehyde. This is glyceraldehyde. This is glyceraldehyde. You have to remember the structure of glyceraldehyde. But can I say this is the Fischer structure of glyceraldehyde? This is also the Fischer structure of glyceraldehyde. And if we number this parent chain, because this glyceraldehyde contains 3 carbons. So this is carbon number 1, carbon number 2, carbon number 3. As per nomenclature is concerned, 3 carbons are there. So 1, 2 and 3. This is second last carbon. This is second last carbon. In this glyceraldehyde Fischer structure, when CHO is present on top, CH2OH is present on bottom. If OH is on right side, we call that glyceraldehyde, as D-glyceraldehyde. And if OH is present on left, but at second last carbon, when CHO is present on top, CH2OH is present on bottom, we call that glyceraldehyde as L-glyceraldehyde. Now, these D and L are taken as standard references. Now, if you have to compare, suppose question is like this: what is the configuration of this? What is the configuration of this? Is this D-glyceraldehyde or L-glyceraldehyde? First of all, we have to check, is this molecule having Fischer structure? Answer is yes. Is this molecule having CHO on top and CH2OH on bottom? Answer is yes. Then number this 1, 2, 3 and 4. Total carbons are 4 in number. Second last carbon means carbon 3. Carbon 3, that means second last carbon is having OH on right. That means it resembles at second last carbon with this structure, OH on right. So this is D, hence this is also D. This is also having D configuration. That means D is not its original configuration. It is the configuration on comparing with standard reference. That is why this is known as relative configuration. I hope this is clear. I hope this is clear. I hope this is clear. Is this clear? Is this clear, my dear lovely students? Now, say for example, you are having a structure like this. This is polyhydroxy ketone. This was polyhydroxyaldehyde. Now, first of all, let me give you one more example over here. Suppose if it is CHO, this is OH, once again OH, then this is CH2OH, here it is H and H. Now tell me, first of all, is this the polyhydroxyaldehyde? Is this the polyhydroxyaldehyde containing at least one chiral center? Answer is yes, like that of this. Now, is this a Fischer structure? Answer is yes. Is this structure having CHO on top? Answer is yes. Is this having CH2OH on bottom? Answer is yes. Now, number this, and check. At second last carbon, where is OH? OH is on left. That means at second last carbon, OH is on left, means it resembles with that of L. So this is L. I hope this is clear. I hope this is clear. After that, in case of, just a moment. In case of polyhydroxy ketone, what we have to do is Fischer, it should be Fischer structure. Then Fischer structure should be such that CH2OH should be on top, CH2OH should be on bottom. But when we number this R C double bond O, that means second position of, say C double bond O should be present at second position but from top. It should be present at second position from top. Then you have to check OH at second last carbon. Second last carbon, OH is present on D, on right side, so this is D. Similarly, if you are having a Fischer structure, polyhydroxy ketone, such that CH2OH is on top, CH2OH is on bottom, but C double bond O group is present at second position from top. Second position from top. Then second last carbon, check second last carbon. If second last carbon is OH on left side, then it is L. Now tell me, by comparing, say other polyhydroxy ketone with this, tell me which type of configuration is this having? Is this having D configuration or is it having L configuration? Tell me, what will be the configuration of this and what will be the configuration of this molecule? What will be the configuration of these two molecules with respect to D and L? What will be the configuration? Have a look. Have a look. Very, very simple. 1, 2, 3, 4, 5. That means this is the Fischer structure of polyhydroxy ketone such that CH2OH should be on top, CH2OH is on bottom, and C double bond O, that means ketone functional group, is present at second position from top. Similarly, this one. Similarly, this one. Then we have to check second last carbon. Second last carbon, OH is on right, so it is D. OH is on left, then it is L. Very, very, very simple. So this is all about D and L. Now, my dear lovely students, there is another term, that is threo and erythro. Now, threo and erythro terms are used for molecules having Fischer structure like this. If molecule is having Fischer structure and it is having different chiral centers, say for example like this. If it is having different chiral centers like this. This chiral center is having different group, this chiral center is having different group. So Fischer structure in which there is a molecule such that say for example a molecule is present in Fischer structure, then it's having chiral centers but different chiral centers such that the identical groups on chiral center 1 and chiral center 2, identical group on chiral center 1 and chiral center 2, they are on same side, we simply call that as erythro form. We call that form as erythro. We call that form as erythro. Similarly, it is CHO, this is CH2OH, once again a Fischer structure. Here it is OH on right, H on left. Now at second chiral center, OH is on left, H is on right. That means identical groups, OH and OH, they are opposite, H and H, they are opposite. So when identical groups are opposite at two different chiral centers in Fischer structure, we call that form as threo form. So this is erythro form, this can be a threo form. Similarly, if I write like this, this is H, this is Br, this is H, this is I, and then this is CH3. We have to check identical groups. Identical groups are on the same side at two different chiral centers. So this is erythro. So this is erythro. Similarly, my dear lovely students, if I write CH3 and CH3 like this, then here it is Br, here it is H, here it is, I and here it is H. HH, identical groups are on opposite side at two different chiral centers. So we can simply say this is threo. So one is erythro, another is threo. I hope this is clear. I hope this is clear. Now, here is another term known as enantiomers. Now, what is meant by enantiomer? Enantiomer means simply compounds which are or stereoisomers which are non-superimposable with their mirror image. But stereoisomers are compounds which are non-superimposable with their mirror image are known as achiral molecules as well as say enantiomers. That means enantiomers are basically achiral molecules. So listen, stereoisomers which are non-superimposable with their mirror image are called enantiomers. Enantiomers are they are also called chiral molecules, not achiral molecules. The enantiomers are also chiral molecules, because what is meant by chiral molecule? When a molecule is non-superimposable with its mirror image. So stereoisomers which are non-superimposable with their mirror image are enantiomers, but they are also chiral molecules because they are non-superimposable with their mirror image. That means they are chiral molecules. After that, enantiomers have similar physical properties like melting point, boiling point, solubilities. That means they cannot be separated easily. They cannot be separated by fractional distillation or fractional crystallization. Enantiomers have same magnitude of rotation but opposite, but they have different direction or sign of rotation. That means if there are two enantiomers, if plane polarized light is passed, both rotate plane polarized light with same magnitude. Say for example, it rotates plane polarized light towards, say right 50 degree, but it will rotate towards left 50 degree. That means magnitude will be 50 degree, but direction or sign will be different. That is what here it is written. Enantiomers have same magnitude of rotation, but different sign of rotation with respect to plane polarized light. And enantiomers may or may not have chiral center. Have a look. Now, first of all, how can we check whether two compounds are enantiomers or not? Listen, both these compounds are enantiomers, but condition is, number one, both these should be stereoisomer. Both must be chiral center. Both must be chiral molecules. Both must be chiral molecules, and configuration at each chiral center should be different. What is meant by that? Have a look. What is meant by that? Have a look. Now, say for example, we are having Br, this is having H, and this is having F. Now, listen, my dear lovely student, this is having one chiral center. Any species which is having one chiral center except amine and carbanions, they are always, say optically active. This is any species which is having chiral center is always chiral molecule, and this is also optically active. Now, if I draw a mirror image of this, listen carefully. If I draw a mirror image of this like this, F, and this is Br, and this is H. Now, these two are having mirror images. Listen, these two are having mirror images. But if I put this on this, if I draw this structure on this, they are non-superimposable mirror images. That means these two are enantiomers. Listen carefully, my dear lovely students. How to check whether these two are enantiomers or not? First of all, both are having same molecular formula. They are having different, say, relative arrangement of atoms or groups around this chiral center. That means they are stereoisomers, point number one. Point number second is both must be chiral. This is having one chiral center, this is having one chiral center, hence both are chiral. Then point number third. Point number third is, what is the configuration of this? This is 1, this is 2, this is 3, this is 4. So fourth priority is present on vertical line. So 1, 2, 3 clockwise means it is R. So it is R. What about this? This is 1, this is 2, this is 3. This is 4. Fourth priority is present on vertical line. So say I have written same. These are not mirror images. I have written same. So F, it should be like this, and Br, it is like this. So this is 2, this is 3. Now, fourth priority is present on vertical line. So 1, 2, 3 is anticlockwise. Anticlockwise means S. So these two compounds are enantiomers. Point 1, reason. Because conditions for enantiomerism is two compounds are enantiomers. First, they should be stereoisomers. They are stereoisomers. Point second, both should be chiral. Both should be chiral because both are having one chiral center. Hence, both are chiral. After that, configuration at each chiral center. Each chiral center, this is R, this is S. Each chiral center should have different, configuration. Hence, these two are enantiomers. These two are enantiomers. For example, if I write like this, this is I, this is Br, this is Cl, and this is F. And I will write down like this. I will write down I will write down, Br, I will write down F, I will write down Cl. So what are these? What is the relation between these two? Have a look. First of all, they are stereoisomers. They are chiral molecules because they are having chiral center 1, 1, 1, 1 chiral center. Now, after that, it is configuration which will decide. So 1, 2, 3, and 4. Fourth priority is present on vertical line. So configuration 1, 2, 3 they are clockwise direction. That means they are having configuration R. They are having configuration. This is having configuration R. Now here, it is 1, it is 2, it is 3, and this is 4. 1, 2, 3 are present in clockwise direction, but fourth priority is present on horizontal line. So clockwise should be R, but it will be S. Now have a look. Both are, stereoisomers, both are chiral molecules, both are having configuration different at chiral center. Hence, these are also enantiomers. They are also enantiomers. I hope this is clear. After that, say for example, you are having a structure like this, CHO, then you are having a structure like this. This is OH, then Say for example, this is OH, then this is H, this is H, this is having CH2OH. Or let me write down over here like this. This is OH and this is H. Now, I will draw two structures over here. One like this, H, H, OH, OH, CH2OH. One like this, another like this, CH2OH, then it is like this, OH, H, OH, H and CHO. Now listen carefully. First of all, this is the chiral center. I will simply give priority to this. Group is 1, this group is 2, second priority, and this whole group, this is 3 with respect to this chiral center, and this is 4. Now, 1, 2, 3. 1, 2, 3 is anti-clockwise. Anti-clockwise should be S, but as fourth priority is present on horizontal line, so this is R. So this is R. Similarly, with respect to this chiral center, this is 1, and above group is, I mean to say 2. Then this is 3, this is 4. Now, 1, 2, 3. 1, 2, 3 is once again anti-clockwise, but it should be R because fourth priority is present on horizontal line. Now, 1, 2, this group is 3 for this chiral center and this is 4. So 1, 2, 3, it is clockwise. Clockwise should be R, but fourth priority is present on horizontal line, so it should be changed from R to S. Now, similarly, what about this? This is 1, above is 2 for this, this is 3, this is 4. So 1, 2, 3 is clockwise. Clockwise should be R, but according to golden rule, it should be S. Now tell me, both these compounds, let us suppose this is compound 1, this is compound 2. So can I say 1 and 2? Both these compounds are what we call stereoisomers, both are chiral molecules, and both are having configuration different at their chiral centers, hence they are enantiomers. Now, what about this one? Listen, this is 1, this one is 2, this one is 3, this one is 4. So 1, 2, 3. 1, 2, 3 is clockwise, R, but it changes to S according to golden rule. Similarly, this is 1, this is 2, above is 3, this is 4. So 1, 2, 3 clockwise, but it changes to, S according to golden rule. Now, listen carefully. Can I say, if this is 1, this is 2, this is 3, can I say a relation between 1 and 3, 1 and 3? 1 and 3. Both are having, listen carefully, both are having, same formula, that means they are stereoisomers in nutshell. Both are chiral, but I have to compare, or we have to compare this. Have a look. We will compare this carbon to which CHO is attached to this carbon to which CHO is attached. Now tell me, is this chiral center in both these having same configuration or different configuration? Configuration has been changed. Now, what about this carbon to which CH2OH is attached? This is S here, this is R here. That means configuration has been changed on both the carbons at all chiral centers. Hence, 1 and 3 are also enantiomers. But what about 2 and 3? With their respective chiral centers, this and this is having S, this is also having S, this is having S, this is also having S. That means they are homomers. If configuration at all chiral centers differ, then it is enantiomer, but provided they are stereoisomers and chiral molecules. But if configuration at every chiral center is same, then we can simply say they are homomers. I hope this is clear. What is meant by homomer and what is meant by enantiomer, this is clear to you. After that, we will be having another, that is diastereomer. What are diastereomers? They are once again stereoisomers, but they are not mirror images of each other. So remember, stereoisomers which are not mirror images, they are known as diastereomers. They have different physical properties. If they have different physical properties like melting point, boiling point, that means they can be easily separated from each other. Then they may or may not be chiral. They may or may not have chiral center as well. Now, Listen carefully. How to check whether those compounds, these compounds, one compound, compound 2, they are diastereomers or not? First of all, they must be stereoisomers. Point number 1, they must be stereoisomers. Point number 2, they may or may not have chiral center. May not have chiral center. Have a look. If I write down like this, we know this is a cis form, this is a cis form, and if I write down its trans form, we know we have already discussed this in previous session. This is its trans form. Now what is the relation between cis and trans? They are basically geometrical isomers, and geometrical isomer means they are stereoisomers. They are stereoisomers, but they do not have any chiral center. So stereoisomers without chiral centers are these. But these are stereoisomers, but they are not mirror images of each other. They are not mirror images of each other. Hence, we can simply say they are diastereomers, because any stereoisomer which are not mirror images of each other, they are known as diastereomers. So geometrical isomers can be diastereomers, but they do not have any chiral centers. That's why they may or may not have chiral center. They do not have chiral center, but if they have chiral center, then diastereomers must contain at least 2 chiral center. They must contain at least 2 chiral centers. Say for example like this. For example like this. For example like this. So either they should not have any chiral center, but if they have chiral center, they must have at least 2 chiral centers. Say for example this and this. Listen carefully. Listen carefully. These two are stereoisomers having chiral center more than 2, but they are not mirror images of each other. They are not mirror images of each other, hence they are diastereomers. So they are diastereomers. So diastereomers may or may not have chiral center. Listen that. But how to identify diastereomer is very, very simple. Configuration at one chiral center in one compound and configuration of same chiral center in another compound, you have to check like that. So at least at one chiral center, at least among these two, at least at one chiral center, configuration in this should be different, and at least at one chiral center, configuration should be same in this. Have a look. When we assign configuration, let me assign configuration directly. This is 1, this one is 2, that is 3. That means it is R changes to S. This one, 1, 2, 3, S changes to R. What about this one? This is 1, 1, 2, 3. It is simply R changes to S. But what about this? 1, 2, 3. It is R changes to S. Have a look. Have a look. If we look towards this chiral center to which Cl is attached, and to this chiral center to which Cl is attached, same type of chiral center in 2 different compounds. This is having S, this is having S. That means this chiral center is having same configuration. But here, chiral center to which Br is attached, in this compound it is R. Chiral center to which Br is attached, in this compound it is S. So one chiral center is having same configuration, another is having different configuration. So at least one is having same configuration, at least one is having different configuration. We will simply say such compounds as diastereoisomers or diastereomers. I hope this is clear. I hope this is clear. After that, my dear lovely students, we have meso compounds. What are meso compounds? Meso compounds are basically those compounds which must contain at least 2 chiral centers, But even though they are having 2 chiral centers, still overall molecule should be achiral. Have a look. What is meant by that? Listen carefully. If I write down I, then it is Br, then it is Cl, then it is Br, then it is Cl, and then I. It's having 2 chiral center, 1 and 1, 2 chiral center. But my dear lovely students, this is having 2 chiral center, but still because of plane of symmetry, because of presence of plane of symmetry, any element of symmetry, whenever any element of symmetry is present in a molecule, molecule is achiral. Because of presence of plane of symmetry, molecule is achiral. So this is simply known as meso compound. So what is meso compound or a mesoform? Meso compound or mesoform must contain at least 2 chiral center, but Because of presence of either POS or because of presence of COS, molecule overall is achiral, then meso compounds are achiral molecules in nutshell. That means meso compounds are those compounds which are achiral in nature, but they must contain at least two chiral center, and their achirality is either because of plane of symmetry, sometimes it is because of center of symmetry, or we can simply say due to internal compensation. What is meant by that? Have a look. If I write like this, this is OH, this is H. Suppose this is, say OH and this is H. This is H and this is OH. Listen carefully. This molecule does not have any chiral, this does not have any plane of symmetry, but this is having a chiral center and a chiral center. And this is the center of this, molecule imaginary center, which divides molecule into, it's that center through which when lines drawn on one side, say for example, if I draw line on, towards OH above the plane and below the plane, that means opposite sides, they are touching identical, groups, similarly touching identical groups, that clearly means that this is having COS is present over here. That means molecule becomes achiral. Molecule is achiral, containing at least two chiral center, is known as meso compound. So this is a meso compound. So what is a meso compound? First of all, tell me that. Meso compound is that compound which contains at least two chiral centers, but still it is achiral, either due to presence of plane of symmetry or due to presence of what we call center of symmetry. Or you can simply say like this. Have a look. This is the chiral center. Its configuration is 1, this is 2, this is 3, this one is 4 for that. That means 1, 2, 3 clockwise, 4 is present on vertical line. That means it remains as it is. So it is R. It is having chiral center is having configuration R. But this chiral center is having 1, 2, 3, and this group is 4. This is having anti-clockwise direction. That means S. So listen carefully. So this is having R configuration, this is having S configuration. Both are having similar or identical groups attached to this. Whatever groups are attached to this chiral center, similar groups are attached to this chiral center. That means when light is passed, plane polarized light is passed through this molecule, this chiral center will rotate plane polarized light with same magnitude as that of this chiral center, because similar groups are attached to them. Now, if it rotates plane polarized light towards right 50 degree, it will rotate plane polarized light towards left 50 degree. Why? Because they are having different configuration. Different configuration means they are having, different sign of rotation. If one rotates towards right, another will rotate towards left. If this rotates plane polarized light towards left, it will rotate towards right. That means there will be cancellation of rotation. If it rotates 50 degree towards right, exact 50 degree towards left will be rotated by this. That means 50 degree towards right, 50 degree towards left, net rotation will be 0. This is known as internal compensation. So in nutshell, meso compounds are those compounds which contain at least two chiral centers, but still they are achiral because of presence of plane of symmetry or center of symmetry or due to internal compensation. Now, how to check compound is meso compound? How to check it's showing, internal compensation? First, there should be at least two chiral centers, and these chiral centers should be identical. That means groups attached to chiral center should be same. After that, one should be having R configuration, another should be having S configuration. Now have a look. If we talk about this, COOH, OH, H, OH, H, COOH. This is also having two chiral centers, but this is having configuration 1, 2, this one is 3, and this is 4. So 1, 2, 3. 1, 2, 3 is anti-clockwise, but I will write down R because fourth priority is present on horizontal line. Similarly, this is 1, this is 2, and for this chiral center, this above group is 3, this is 4. So 1, 2, 3. 1, 2, 3 clockwise, but it should change to S according to golden rule because fourth priority is present on horizontal line. Have a look. This chiral center and this chiral center have similar groups attached to it. Hence, Whenever you are having two chiral centers present in a molecule and both are identical, I mean say having similar groups attached to them, then one is having R configuration, another is having S configuration, we will simply say this is a meso compound. This is a meso compound. This is a meso compound. If I write like down, if I write molecule like this, if I write down the molecule like this, this is also a meso compound. This is also a meso compound. How? Have a look. 1, 2, this one is 3, this is 4. So this is 1, 2, 3 R, but it changes to S. This one 1, and with this, with respect to this chiral center, this is 2, and this one is 3, this is 4. So 1, 2, 3 anti-clockwise, this is R. So S and R and groups are same. That means once again a meso compound. But these two are, check, these two are mirror images of each other. So whenever you are having two meso compounds which are having same formula or which are having mirror images of each other, remember their relation is always they are identical or they are homomers. They are homomers of each other. That means a mirror image of a meso compound is also a meso compound. That means both are homomers. If you put this on this, they will simply coincide. They will simply coincide. Why? Because they are homomers of one another. Now, so these are the points which are written over here. Listen carefully. Compounds which contain at least two chiral center but are still achiral molecules, such molecules are known as meso compounds. Such compounds are superimposable with their mirror images. Remember, meso compounds and their mirror images are homomers of each other. Mirror image of a meso compound is also a meso compound. Then meso compounds are achiral, hence optically inactive due to internal compensation or presence of plane of symmetry or center of symmetry. In nutshell, meso compound must contain meso compound must contain at least two chiral center, and after that they are still what we call achiral molecules. Now, have a look. Have a look, my dear lovely students. Now tell me, what will be the configuration of first? What will be the configuration of this? This is 1, methyl, this ethyl is 1, methyl is 2nd, deuterium is 3rd, and hydrogen is 4th. So 1, 2, 3 is clockwise, but I will write down S for this because clockwise means R, but as 4th priority is present on horizontal line, so use golden rule, so R changes to S. What about this? This is 1, this is 2, this is 3. 4th priority is present on vertical line. So 1, 2, 3. 1, 2, 3 is clockwise. So never use golden rule over here. So this is R. One is S, another is R. Both are stereoisomers. Both are stereoisomers. Both are chiral molecules, but both are having different configuration at chiral center. Hence they are enantiomers of each other. Have a look. Chiral center and chiral center. Both are having stereoisomers, both are chiral molecules. Now, check configuration 1, 2, 3 and 4. 4th is present on dash bond. So 1, 2, 3 is anti-clockwise. So this is S. What about this? 1, 2, 3 and 4. Now listen, 4th is not present on horizontal, not present on dash bond. What we have to do is we have to interchange. Let me interchange over here. Have a look. We have to interchange 4 and 3. So 4 should be present on dash. Then here it will be 3. 1 and 2 will be on, say the same position. So 1, 2, 3. 1, 2, 3 is now anti-clockwise. That means this is S. Now this is S, but this is S after one interchange. Hence this will be R. Actual molecule is R because after interchange it becomes S. So S and R. One is S, another is R. So they are enantiomers. Now have a look. You can have a plane of symmetry over here. Simple. Plane of symmetry. As plane of symmetry is here, so plane of symmetry is present. So this is a meso compound. Now, when it is not visible that plane of symmetry is there or not, you can use RS as well. But here it is clear. Plane of symmetry is there. Because of plane of symmetry, it becomes meso compound. Now why it becomes meso compound? Because due to plane of symmetry, it becomes achiral. But this is having 2 chiral centers, so compound having at least 2 chiral centers, and after that it is having, say it is achiral, then these are meso compounds. So both are meso compounds. This meso compound and this meso compound, they are identical or they are homomers, because both are having same molecular formula or they are mirror images of each other. Now, what about this? What about this? There is no plane of symmetry. That means there is no plane of symmetry, and in such molecules center of symmetry is also absent, hence such molecules are chiral molecules. So stereoisomers, chiral molecules. Now we have to check configuration. This is 1, this is 1, this is 2, and this one is 3. So 1, 2, 3, 1, 2, 3, anti-clockwise. Anti-clockwise means this is S, but it should be changed to R as 4th priority is present on horizontal line. Now 1, then this one is 2, this one is 3. So once again anti-clockwise, it changes once again to R. Now this one, it is once again anti-clockwise, but anti-clockwise changes to R. What about this? Once again anti-clockwise, anti-clockwise changes to R because of golden rule. So having same molecular formula, same configuration, hence they are homomers. Homomers. What about this? Have a look how to simply answer this question. You can answer the question with the help of, say RS configuration, but you can also answer this question like this. This is the chiral center. This is the chiral center. If we number the parent chain, this is 1, 2, 3, 4, and 5. Now, if we number the parent chain, this is 1, 2, 3, 4, 5. Now tell me, at this chiral center, carbon 1 is on left, carbon 2 is on right. Here, left and right are same. But here, chlorine is below the plane and hydrogen, which is hidden, is above the plane. Here, chlorine becomes above the plane, hydrogen, which is hidden, that becomes below the plane. That means above becomes below, below becomes above. Only one interchange has been taken place at this chiral center. Listen carefully. At chiral center 2, in these two compounds, one interchange has been taken place. Whenever even number of interchange takes place at one chiral center, configuration remains same. Remember it. But if odd number of interchange takes place at one chiral center, configuration changes. That means its configuration should be different. You can check that as well after giving priorities to these groups. So these two are having different configuration. What about this and this? These two are also having different configuration because one is above the plane, another is below the plane. One interchange at one chiral center changes the configuration because that is odd number. Similarly, this is also having different configuration. So every chiral center is having different configuration, and overall molecules are stereoisomers as well as chiral, hence they are enantiomers of each other. They are enantiomers of each other. What about this? What about this? Listen carefully. This is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So left and right, they are same, but below becomes above, above becomes below. That means one interchange. One interchange means configuration at this chiral center is different. What about this? Below becomes up, below remain as it is. That means configuration does not change. So at chiral center 2, configuration is different. At chiral center 3, configuration is same. What about chiral center 4? Chiral center 4 is also having configuration same. That means these are the two compounds in which there is at least one chiral center where configuration is different and at least one chiral center where configuration is same. Hence they are diastereomers of each other. So they are diastereomers of each other. I hope this is clear. I hope this is clear. After that, my dear lovely students, a very simple example is a simple definition is epimer. What is meant by epimer? These are the stereoisomers which differ in configuration only at one chiral center, and that chiral center can be anyone. So whenever stereoisomers differ in their configuration at one chiral center only, that means other chiral centers should be having same configuration. That means such compounds are known as epimers, but can I say such compounds are also known as diastereomers as well? Because what is meant by diastereomer? Which is having configuration different at least at one chiral center. This is having configuration different at least at one chiral center. This is having configuration similar at other chiral centers. That means at least at one chiral center configuration is also similar. That means epimers are always diastereomers. So have a look. If I number this molecule like this, if I number this, it's like this: 1, 2, 3, 4, 5, 6. This is 1, 2, 3, 4, 5, 6. Now have a look. If we relate 1 and 2, what is the relation between 1 and 2? What is the relation between 1 and 3? What is the relation between 2 and 3? Let's relate them. Now, if we relate this 1 structure with 2, at chiral center 2, configuration is different because here OH is present on right, here OH is present on left. That means configuration is different at, say chiral center 2. But chiral center 3, chiral center 4, chiral center 5 are having similar configuration. That means these two compounds are those stereoisomers which differ in their configuration but at only one chiral center, and that chiral center is carbon 2. So they are C2 epimers, because it is the only chiral center 2 where configuration has been is different with respect to each other. Hence they are epimers, but epimers because of chiral center 2. Now, what is the relation between 1 and 3? What is the relation between 1 and 3? Have a look, have a look. Now let me use another color. If we check carbon number 2, here carbon number 2 is, having same side. That means it's not having any different configuration at 2, not at 3, not at 4, but it is 5. It is 5. It is chiral center 5. Chiral center 5 is having different configuration. Chiral center 5 is having different configuration because one is having chiral center OH on 5 side at chiral center 5 and another is having OH on left side. That means they are, 1 and 3 are C5 epimers because others are having same configuration. So these two are epimers. 1 and 2 are epimer, that means they are also diastereomer. 1 and 3 are epimer, that means they are also diastereomer. But what about 2 and 3? What about 2 and 3? Have a look. At chiral center 2, they are having different configuration. They are having different configuration at chiral center 2 as well as chiral center 5, as well as chiral center 5. Have a look. So they are having different configuration, but at more than one chiral center. That means they are not epimers, but they are diastereomers. How they are diastereomers? Listen. They are diastereoisomers, diastereomers, but they are not epimers, because epimer means if they are having different configuration only at one chiral center, but these two are having different configuration at least at two chiral centers. So now, why they are diastereomers? Because at least at one chiral center, they are having different configuration. At least at one chiral center, they are having similar configuration. So they are diastereomers. But these are epimers as well as, they are diastereomers as epimers as well as diastereomers. They are epimers as well as diastereomers. So can I simply say that all epimers are diastereomers? All epimers are diastereoisomers or diastereomers, but all diastereomers are not epimers. Remember this one. Remember this thing. Remember this thing. Now, after that, there is another part, that is calculation of stereoisomers. Remember, when molecule is unsymmetrical, number of optically active isomers, that means enantiomers, is 2 raised to the power n. Optically inactive forms, that means meso forms, are at that time equal to 0. Total stereoisomers will be at that time 2 raised power n, and enantiomeric pairs will be always enantiomer divided by 2. If enantiomers are 4, that means pair will be 4 divided by 2 means 2. So what is this n? N means number of optical isomer over here, because we are talking about optical isomerism. Now, after that, when molecule is symmetrical, at that time there are two cases. One, and if n is even, that means if number of optical isomer area is even, and if n is odd. If n is even, E is equal, enantiomers is equal to 2 raised power n minus 1, M is equal, that means mesoforms at that time, optically inactive forms will be 2 raised power p minus 1, total will be 2 raised power n minus 1 plus 2 raised power p minus 1, and p here is equal to n by 2 because n is even, and enantiomeric pairs will be always e by 2. And if n is odd, at that time E is equal to 2 raised power n minus 1 minus 2 raised power p minus 1, and m is equal to 2 raised power p minus 1, and E plus m is 2 raised power n minus 1. That means p here is n plus 1 divided by 2. So these are the formulas. Now you can use these formulas over here. Have a look, my dear lovely students. This is the chiral center, this is the chiral center, and this is the chiral center, this is the chiral center. Or chiral centers are always optically active optical isomer areas. Basically, this is the area due to which optical isomerism occurs. So this is optical isomer area, optical isomer area, optical isomer area, optical isomer area. So here n is equal to 4, optical isomer areas are 4, and this molecule is unsymmetrical because it cannot be divided into two equal halves such that one half is exactly mirror image of another. So this is unsymmetrical. Now for unsymmetrical, we know total E plus m, total say stereoisomers, that means E plus m, enantiomers plus mesoforms is simply equal to 2 raised power n. Have a look, have a look, have a look. For unsymmetrical, total forms E plus m is 2 raised power n. Now use the value of n, you can answer me the question. So this is very, very simple. So it is 2 raised to the power 4. So 2 raised power 2 is 4, 2 raised power 3 is 8, 2 raised power 4 is 16. So it is 16. Similarly, OI area 1, OI area 2, OI area 3. So n is equal to 3. Molecule is unsymmetrical. So you can simply use here formula, that is E plus m will be equal to 2 raised power n. That means 2 raised power 3. Answer is 8. Here, my dear lovely students, this is 1, this is 2, this is 3, this is 4. Once again, a similar structure like this. So here, n is equal to 4. Once again, this is unsymmetrical. Formula becomes E plus m is equal to 2 raised power n. So the answer is 2 raised power 4. Once again, it is 16. Very, very, very simple. What about this? We know this is what we call n. This is the optical isomer area. So n here is 1. Whenever n is 1, never use formula. Write directly that E plus m here is equal to 2. That means total isomers here will be equal to 2. Now, total isomers will be equal to 2. Now you can check which type, will be, how many will be their meso compounds and how many will be their, this enantiomers or optically active forms. Or you can simply say total isomers will be simply what we call 2. Similarly, this is 1, this is second. So 2, n is equal to 2. But molecule is unsymmetrical. So it is simply E plus m, or total isomers will be 2 raised power n, that means 2 raised power 2. So answer is 4. Here, this is 1. This is another, because this is the chiral center, this is chiral center. Chiral centers are always, OI areas. This is also OI area. This is also OI area. And after that, this is also the OI area. So 1, 2, 3, 4, 5, 6. So you can simply write down n is 6. It's unsymmetrical. Now after that, you can calculate this. You can calculate this. After that, my dear lovely students, just a moment. Give me a second. Give me a second. Say for example, you are having a structure like this. For example, you are having a structure like this. You are having a structure like this. This is having 1, 2, and 3 optical isomer areas. 2 are, chiral centers, and 1 is pseudo-chiral center. In nutshell, their n is equal to 3. Molecule is symmetrical. This is not unsymmetrical, it is symmetrical. You can divide it. This part and this part will be, identical. So molecule is symmetrical. At that time, E plus m, 1, once, n is 3. n is 3 means n is odd. N is odd. N is not even. N is not even. When n is not even, it is simply 2 raised power n minus 1. Have a look. Have a look. it is 2 raised power n minus 1. When n is odd. When n is odd, it is 2 raised power n minus 1. So 2 raised power n minus 1. What is n? N is 3. So I will write down 2 raised power 3 minus 1. 3 minus 1 is 2. So it is 2 raised power 2. Answer is 4. Is this clear? Is this clear? Is this clear? Why its answer is 2? Have a look. Have a look. Have a look. Have a look. Whenever n is odd, symmetrical n is odd, at that time E is 2 raised power n minus 1. N was 3, so 3 minus 1 is 2, 2 raised power 2 is 4. So this is the answer. Similarly, if you are having a structure like this, CH3, CH, CH and CH3. This is OH, this is OH. What is the value of, I mean to say, n over here? N here is 2 and this is also symmetrical. So this is symmetrical. When it is symmetrical, n is 2, but here n is even, it is not odd. Then E plus M, total isomers, total stereoisomer here will be, it's E plus M. E plus M here is 2 raised power n minus 1 plus 2 raised power p minus 1. But n is given, so what is p? What is p? When n is even, p is equal to n by 2. N is 2. So I will write down 2 divided by 2, answer is 1. So what will be the value of, I mean say E plus M? 2 raised power, n is 2, 2 minus 1. Then 2 raised power p, p is 1, so 1 minus 1. So it is equal to 2 raised power 1, so it is 2, plus 2 raised power 0, anything raised power 0 is 1. So the answer is 3. It's very, very simple. Very, very, very simple. I hope this is clear. After that, my dear lovely students, it is racemization. What is meant by racemization? Process of formation of racemic mixture is known as the racemization. What is racemic mixture? It is simply an optically inactive mixture which is obtained by mixing equal proportions of optically active enantiomers, or by mixing of two optically active enantiomers in equal proportions. Then it is optically inactive because of external compensation. It is denoted by DL, small dl, or plus minus, or sometimes it is denoted by RS. What is meant by that? Have a look. Have a look. Say for example, suppose we are having a compound like this. What is the configuration? What is the configuration of this one? It is 1, this is 2, this is 3, this is 4. So its configuration is 1, 2, 3 clockwise. Clockwise means R, it remains as it is because fourth priority is present on vertical line. Similarly, when plane polarized light is passed through it, as it is a chiral molecule optically active, that light, plane polarized light, gets deflected. That means it rotates plane polarized light, hence it is optically active. But if we talk about this one, this is Br, this is Cl, this is F. Once again, a chiral center is this. Overall molecule is chiral molecule. This is optically active molecule. And when plane polarized light is passed through it, it also deflects or rotates plane polarized light. That means this is also optically active molecule. And these two are stereoisomers. These two are chiral molecules. And these two are having different configuration. That means these two are enantiomers. These two are enantiomers of each other. And listen carefully. This is optically active. This is optically active. But when we add these and form a mixture, when we form a mixture of these two, when we form a mixture of these two enantiomers, or we form a mixture by mixing two enantiomer in equal proportions, then if plane polarized light is passed now, it will rotate plane polarized light in one direction with some magnitude. It will rotate same plane polarized light in opposite direction with same magnitude. Suppose it rotates plane polarized light towards right 50 degree, it will rotate towards left 50 degree. That means net rotation of plane polarized light will be 0. That means if there is no rotation of plane polarized light on passing through this mixture is simply known as racemic mixture, and this racemic mixture is optically inactive. So what is racemic mixture? Racemic mixture is simply mixture which is obtained by which is obtained by mixing two optically active enantiomers. This is optically active because light it rotates plane polarized light. This rotates plane polarized light, and they are enantiomers. Enantiomers are optically active. So when two optically active enantiomers are mixed together in equal proportions, it forms a mixture which is overall optically inactive, because one molecule rotates plane polarized light and another molecule, another external molecule compensates that rotation, cancels that rotation, and net rotation of plane polarized light is zero. Hence, this is optically inactive mixture, and this optically inactive mixture is known as racemic mixture. Suppose this is dextrorotatory, this is levorotatory, this is simply DL. Suppose this is R, this is S, we can simply say mixture is RS. If this is dextrorotatory, this is levorotatory, that means one is plus, another is minus. So this is basically how we can represent this, say, racemic mixture. Now listen, if this is the racemic mixture, separation of this optically active enantiomer and this optically active enantiomer from its own racemic mixture, that process is known as resolution. That process is known as resolution. That means our another topic is resolution. Another topic is resolution. So what is meant by resolution? Resolution is simply process of separation of two optically active enantiomers from its own racemic mixture. Remember, the enantiomer which is separated out is known as resolvable compound, and resolvable compound or resolvable components are always optically active. So this is all about resolution. So process of separation of two optically active enantiomers from their own racemic mixture is called resolution. The enantiomer which is separated out from its own racemic mixture is called resolvable compound, and resolvable compounds are optically active molecules. So beta, this was all about optical isomerism. Now the another topic, another chapter is simply what we call is haloalkanes and haloarenes. But before doing haloalkanes and haloarenes, let me know in the chats, is optical isomerism clear till now? Is optical isomerism clear till now? Let me know quickly. Tell me, quick, come on. Let me know in the chats, is this clear? Is this clear? So that we can start another chapter. After haloalkanes and haloarenes, there will be a break, but first we will complete haloalkanes and haloarenes. Come on, everyone. So, should we start? How is the Josh for another chapter, that is haloalkanes and haloarenes? How is the Josh for this chapter, my dear lovely students? How is the Josh for this chapter known as haloalkanes and haloarenes? An important chapter. Come on. This is an important chapter. Should we start? Total, say complete class 12th organic chemistry, say today's session will be of 8 to 9 hours of maximum 8 to 9 hours. That means up to 10 or you can say 10:45 p.m. or 11 p.m. maximum. Now, tell me, is this clear? Is this clear till now? So should we start haloalkanes and haloarenes? Let me know in the chats quickly. Let me know quickly. Should we start? Come on, everyone. How is the Josh? Come on. How is the Josh, my dear lovely students? Come on, tell me. Let me know in the chats quickly. How is the Josh? Is Josh still high or not? Come on. Show some green hearts as well. Come on. Come on. Everyone. I will give you a small break, but after this chapter. Come on, my dear lovely students. Come on, everyone. Yes, yes, yes. Come on, come on, come on, come on. So let's start. Let's get started without wasting time. Come on. Come on. So, methods of preparation of haloalkanes from, I mean to say, alcohols first. First of all, from alcohols. From alcohols. Methods of preparation of haloalkanes from alcohols. Have a look. Have a look. Methods of preparation of haloalkanes from alcohols. Listen carefully. If you are having an alcohol, and haloalkane is obtained from that, what we have to do is, we have to remove just this OH, and instead of this OH, we have to add X. That means X should replace OH so that we will get haloalkane. So remember, these types of reactions are examples of nucleophilic substitution reactions. These are examples of substitution nucleophilic or nucleophilic substitution reactions. Now, first of all, let me tell you reaction number 1 of this. Let's have reaction number 1. Reaction number 1 is simply, reaction number 1 is reaction of alcohol with HX. Let me write down over here, this is alcohol and this is HX. Whenever alcohol reacts with HX, we get RX plus water. And listen carefully, very, very important point. This reaction is generally an example of SN1 reaction. This is unimolecular nucleophilic substitution reaction or substitution nucleophilic unimolecular reaction. For example, if we are having an alcohol, in this alcohol, this OH is not a good leaving group, so we can say it's a poor leaving group. On treatment with HX, what will happen first? Have a look. It will get protonated. That means protonation of alcohol takes place in first step, and it will result in the formation of an oxonium ion or a protonated alcohol. Now, this is a very good leaving group. So this is a good leaving group. Now after that, what will happen? Listen carefully. This bond will be broken and it will leave as water molecule. And this step is the slowest step, hence rate determining step of the reaction, and it will result in the formation of a carbocation. So as intermediate is carbocation, we have to rearrange it if possible. Rearrange if possible. After that, my dear lovely students, then another step is that nucleophile X minus will attack, and this is a very fast step, rate independent step, and we will get RX. But listen carefully, this alcohol generally takes place like this. This reaction generally takes place via formation of carbocation. That means this is SN1 reaction. But listen carefully, this R should be equal to tertiary or it should be secondary. That means secondary alcohols and tertiary alcohols generally show this type of reaction known as SN1 reaction, in which alcohol gets alkyl halide or haloalkane. I hope this is clear. But primary alcohols generally, or first of all, let me write down over here. Among alcohols, reactivity order towards this reaction will be it will be 3 degree alcohol. After that, it will be 2 degree. After that, it will be 1 degree alcohol. Why is it so? Because 3 degree alcohols can form much more stable carbocation, as stability of carbocation rate depends on stability of carbocation, because carbocation is formed in RDS. So alcohol which forms more stable carbocation can show much faster reaction. That's why 3 degree alcohol show faster reaction as compared to 2 degree, as compared to 1 degree. This is point number 1. Now, after that, point number 2 is, among halogen acids, among HX, I mean to say, reactivity order towards this reaction is, have a look, that is HI greater than HBr greater than HCl greater than HF. As bond dissociation energy of HF is very, very high, it generally does not show this reaction. So it is simply HI, HBr and HCl. I hope this is clear. After that, my dear lovely students, listen carefully, because this is very, 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 very important reaction. Now, after that, I will simply say that primary alcohols generally prefer this reaction via SN2 mechanism. So secondary and tertiary favor this reaction, or generally takes place this reaction via SN1 mechanism, but primary alcohols generally take place via SN2 mechanism. But there are few primary alcohols, say for example N-butyl alcohol, that undergoes via SN1 reaction, because N-butyl alcohol cannot not N-butyl alcohol, I mean to say this one, neopentyl alcohol, like this. This is the neopentyl alcohol, not N-butyl alcohol. Neopentyl alcohol generally do not show this reaction via SN2. This reaction, this is the neopentyl group. This is a primary alcohol. Primary alcohol generally shows reaction via SN2, but neopentyl alcohol does not show SN2 reaction. That's why it shows reaction via SN1 mechanism. So I will write, erase this, but other primary alcohols generally favor this reaction via SN2 mechanism. Now have a look. If you are having ROH, once again this is a poor leaving group, but this R here is 1 degree generally, but it should not be neopentyl alcohol. Now have a look. This reacts with HX first of all, and it will result in the formation of what we call a protonated alcohol. So it will result in the formation of a protonated alcohol. This is a good leaving group. But if this R is primary, it will not leave first, because primary alkyl cannot form that much stable carbocation as secondary or tertiary forms. That is why here X minus will attack. That means this bond formation and this bond breaking takes place simultaneously. So that's why this reaction is SN2 reaction or SN2 mechanism. So it is like this. So primary alcohols generally show reaction via SN2 mechanism, except say for example neopentyl alcohol, because that is a primary alcohol, but that neopentyl alcohol is a primary alcohol but cannot undergo SN2 reaction. That's why it undergoes SN1 mechanism. But generally, in general, primary alcohol show SN2 mechanism and secondary and tertiary alcohol show SN1 mechanism. Now, after that, my dear lovely students, if we talk about this one, reaction of alcohol with HCl. If we talk about reaction of alcohol with HCl, now what will happen over here? Listen carefully. If we talk about reaction of alcohol with HCl, if we treat primary alcohol with HCl, we know among HCl, HBr, HI, HCl is least reactive, and among 1 degree, 2 degree and 3 degree alcohols, 1 degree alcohol is least reactive. That's why they will not react. They will not react. They need, say some catalyst over here. Let's suppose anhydrous zinc chloride. But this catalyst, in presence of this catalyst, reaction does not take place. So there will be no reaction at room temperature. So primary alcohol, very less reactive, HCl, very less reactive, and even we use zinc chloride, still reaction does not take place. After that, if we write down over here a secondary alcohol, over here, which is more reactive as compared to primary alcohol, it will react now with HCl. But listen carefully. It will undergo SN1 mechanism because it is a secondary alcohol, and it needs this catalyst. So at room temperature, what will happen? It will simply first react with H, and it will lost as OH2 positive. Here it will be a carbocation, then Cl minus will attack that, and it will result in the formation of alkyl chloride like this. And listen, my dear lovely students, product is formed, but once this alkyl chloride is formed, white or milkiness or cloudiness is appeared, that is known as turbidity. So here turbidity appears. Turbidity appears mean this product formation takes place. As there is no reaction, no product formation, so I will say no turbidity appears. No turbidity appears. I will say here no turbidity appears. But here turbidity appears. Turbidity appears after few minutes. After, say for example 5 to 10 minutes. That means after few minutes turbidity appears. That means product formation takes place, but not immediately, after few minutes. After that, if we talk about tertiary alcohol, listen carefully. This tertiary alcohol reacts with this HCl and anhydrous zinc chloride at room temperature. Then what will happen? OH will be lost, carbocation is formed, Cl will be attack that. That means product formation takes place like this. Product formation takes place. It will be water, Okay, that means product formation takes place, which means turbidity appears. Turbidity appears. But not after few minutes. But turbidity appears in seconds. That means turbidity appears immediately. Turbidity appears immediately. That means after seconds. Now, can I say simply here no turbidity appears. Turbidity appears, but after some time turbidity appears immediately. That means this turbidity, appearance of turbidity, is basically dependent on reactivity of alcohol. And reactivity depends on stability of the carbocation formed in RDS. As we know, this forms a very stable carbocation. That's why turbidity appears very fast, which clearly indicates, listen carefully. That means appearance of turbidity is actually proportional to reactivity of alcohol. And reactivity of alcohol is directly proportional to stability of carbocation formed in RDS. So this is very important, my dear lovely students. This point is very important. So any alcohol which can form a very stable carbocation, like resonance stabilized or aromatic carbocation or this tertiary carbocation. So any alcohol which can form a stable carbocation gives, say turbidity immediately. So turbidity is dependent on this thing. I hope this is clear. But among 1 degree, 2 degree and 3 degree alcohols, normal 1 degree, 2 degree, 3 degree alcohols, it's 3 degree alcohol which forms turbidity immediately. And listen, one more thing, very important thing is that this mixture of HCl, HCl and zinc chloride, this mixture, this is known as Lucas reagent. This is known as Lucas reagent. And remember, with the help of this Lucas reagent, with the help of this Lucas reagent, we can distinguish primary, secondary and tertiary alcohols. With the help of Lucas reagent, we can distinguish primary, secondary and tertiary alcohols. How? Say for example, we have doubt that our test tube contains primary alcohol, secondary alcohol or tertiary alcohol, but we don't know which alcohol is this. We know this can be primary, secondary or tertiary, but we are doubtful whether it is primary, we are doubtful whether it is tertiary or secondary. So we want to confirm whether it is a primary, secondary or a tertiary alcohol. So we will add anhydrous zinc chloride and HCl to this. That means Lucas reagent to this. If turbidity appears immediately, we will say this test tube contains tertiary alcohol. If turbidity appears after some time, we will say this secondary alcohol. If there is no turbidity, we will simply say it's a primary alcohol. So